Hello, this is Michael Guess. I am VP Research and Clinical Applications for Persist Development, and this ad hoc screencast will go over some of the quantitative measures that can be used to look for changes in amplitude, changes in frequency, symmetry, and also the use of some of the new statistical tools to compare differences from baselines, user-defined baselines in the EEG. To do this, we're going to use this recording that's a carotid endarterectomy and look for ways to represent changes post-clamp and some other changes in the EEG. This is the beginning of the recording. Let's go ahead and bring up the trends. We can get just an overview of what we expect to see in the underlying recording. This is with artifact reduction off. There's some places in the recording. Let's go ahead and split the screen where we've got artifact from electrosurgical units and moving the patient and so forth. So let's go ahead and click on the AR button where there's not signal to be recovered, where there's excessive electrode artifact and whatnot. We'll go ahead and dash those out. And on the trends, it'll blank if more than half of the trends, channels that comprise a trend are contaminated with electrode artifact. We'll go ahead and blank those trends out at that point. So in most cases, when you're looking at these sorts of analyses, you'll want to use the artifact reduction. Let's go ahead and zoom out. Put 4 hours on. We can look at the recording, this particular recording in its entirety, just to get some landmarks. And let's go ahead and change the gain here. It's low amplitude EEG. We'll start out at 5 microvolts. And this is the beginning of the recording where the patient is most likely awake. And then we go a little bit further on. There's some changes associated with anesthesia. This is a subset of the comprehensive panel. We're just looking at FFT spectrograms left and right from 0 to 20 hertz. Taking the square root values of those. If we click on the scale legend here, we can change the scaling if we wish to make it either lighter or darker. One of the reasons we use square volt scaling, and that could be changed, but one of the reasons to use square volt scaling is amplitude in the delta range tends to be much higher than what you'll see in the alpha and beta ranges. And by trending the square root values of that, it'll reduce the amplitude of the very large amplitude delta and make it a little bit closer to what we see in the beta range, so that without rescaling it a lot, you can see changes in the delta and the beta range simultaneously. Okay. First thing is this is where they've clamped. We can see in the FFT spectrogram some differences here. Let's zoom in a little bit more. We'll go down to an hour. Again, pre-clamp, post-clamp. Let's go ahead and drop the gain a little bit more, down to 3 microvolts. Change the time scale, 10. We'll go to 15 or 20, 15 seconds would be good. What is the difference between this point and this point? Well, pre-clamp and post-clamp. You can see that post-clamp there's a loss of amplitude overall, and according to the FFT spectrogram visually on the traces, we can see that theta to alpha range is lost a bit more so than anything else. So let's see what we see in the trends. FFT spectrogram, again, we see this loss of the brighter colors here post-clamp in that theta to alpha range. We see that reflected in the waveforms. Asymmetry spectrogram looks like it could be just subtracting one from the other, showing the difference between left and right hemisphere. It does a little more than that. It's actually comparing homologous pairs of electrodes in a full 1020 bipolar montage and looking at the amplitude by frequency from 1 to 2, 2 to 3, 3 to 4 hertz, all the way up to 20 hertz. And between those homologous pairs, if it's higher in amplitude on the right, it becomes right-weighted. Higher amplitude on the left, it becomes left-weighted. And that's where we see these plus 50%, minus 50%. Positive values are rendered in red, which means right-weighted. Negative values are rendered in blue, which means left-weighted. If it's red, it's higher in amplitude on the right. And this is pretty evenly higher in amplitude across the clinical power spectrum. And then post-clamp, we can see it's the asymmetries concentrated in that theta to alpha range. Well, with relative asymmetry, we can see that we have change where left is predominant versus right. Well, the question naturally is, well, did the left become more prominent or did the right fall away? That's where the AEG trend or any amplitude trend really can be helpful. In this case, we see that we've lost amplitude overall. If we look at the AEG trend, 0, 10, 50, 75, 100 microvolts. So we're looking at 0 to 10 microvolts at this lower half of the scale. And we're showing left and right overlapped, right hemisphere in red, left hemisphere in blue. And the red is higher in amplitude, the right, than the left. And by laying these on top of each other, we get a pink color where we have amplitude symmetry. And this red fringe at the top just means the right is higher in amplitude. We lose amplitude on both, but post-clamp, we see a blue fringe here. That means the amplitude is higher on the left than the right, even though we've lost amplitude overall. And that gives us some context to look at the asymmetry spectrogram and say, well, the left didn't become higher in amplitude. They both fell, and the right fell more so. Okay, so there's our landmarks in the recording. We'll look at one more where things stabilize a bit. We can click throughout this and see that things are pretty stable. The amplitude of the EEG is has fairly good symmetry, slightly higher in the left. And then we see this darker patch over here. Did the left become more prominent? In comparison to the right, it did. But how did it do that? It wasn't that the left increased in amplitude, it's that we lost amplitude on the right. So this is this blue fringe showing up at the top. That means that when we look at that, right across us, move it just a little bit over here. Left is staying pretty consistent in amplitude all the way across. But we see the shallowing out. We lose this overlap here. That means the right's falling away. And that changes most predominantly in that theta to alpha range. Okay, so now we know where we're looking at the recording as we look at some of these trending options. FFT spectrogram, asymmetry spectrogram, AEG, there's other trends as well. We'll just focus on these as far as looking at frequencies in this particular view. These values can be viewed by right-clicking on the scale legends on the far right, show values. Then wherever I click, I'm going to get the numeric output from that. Now, in the case of an AEG trend, we've got the amplitude on the left, the amplitude on the right. So as we click along here, we can see that the amplitude is falling between here and here. Pretty easy. If we look at the asymmetry spectrogram, we've got 20 bins, 20 frequencies from 1 to 20 hertz. And so to output the values of that at the cursor position, it's going to show you the maximum asymmetry and at what frequency that asymmetry is peak. So if we click post-clamp, it's saying that the maximum asymmetry is minus 27.5 hertz. Here's 12 hertz. Ideally, it's a little bit easier to look at these as time series. So to export these, what we can do is highlight the trend, insert a range, and export these to a CSV file. Now, an easier way to turn these into a single number is to look at an asymmetry index. Let's go ahead and switch to an alpha-delta ratio trend for this recording. Here we're looking at ADR's averaged 2-minute running average. And interestingly, we don't see a lot of deflection in the ADRs. This is a really patient-specific thing as far as whether you'll see them deflect a lot or not. In this case, the amplitude of the EG is low to begin with. There's not a lot of alpha, 8 to 13 hertz power, regardless. And so we don't see a lot of change in the ADRs in this particular one. Again, that'll vary depending on the patient. But we do see pretty prominent changes in the relative asymmetry spectrogram. So how do we turn this into a single number? So the trends below this, navigate back to where I wanted to be. The trends below this are absolute index and relative index. All that's doing is taking all the values and making them positive and showing you the values at that point. And the relative will take them whether they're negative or positive, and you get the sum of those. And here we see that they're mostly positive because they're right-weighted. And then post-clamp, we see this shifts from positive to negative, indicating that it's left-weighted. Interestingly, the overall level of asymmetry doesn't change a lot. The biggest change is seen in that it shifts from one hemisphere to the other. That's just the nature of looking at relative asymmetries. So go a little further along during that subsequent change where we have another loss of faster frequencies over a little bit longer period of time. That dark patch is represented by a swelling of the symmetry index. We see an increase in negative values for the relative and a slight increase in the absolute values. So if we want to export these, what we do is we try to keep the screencast from shifting it around too much. All right, let's right-click on this. We'll go to Insert Range. We'll bracket the area of interest. Highlight the trends we want to export. In this case, we want both the absolute and relative. We hit the Shift key or the Control key. We highlight both of those. So now it's going to restrict our export to the range that I've marked and the two trends that I've highlighted. Let's go to Tools, Export Channel Trend Values, and I'll just overwrite the one I already have, and I've exported those values. So what do we get? Let's go ahead and bring it up in a spreadsheet. I'm going to switch the screen here quickly. Here's a spreadsheet with that opened. Columns to look at is the clock date time. Probably not going to use that very much. It is Microsoft OLE time. The next is the time column. That's going to be more useful. That can be configured from the Preferences dialog. You go to Preferences, General Preferences. You can set the time format. In this case, this is set to elapsed time. And so these are the number of seconds from the beginning of the recording. And we can see these have to be incrementing every 8 seconds. Now, the amount they increment depends on the trend. If you're exporting AEG, it would increment every 1 second. That's its epoch length. Since we're exporting FFT values, admittedly, those are derived. The asymmetry values are derived from the FFT power values, and those epoch lengths are 8 seconds. Those can be configurable. In the default configuration, the FFT epochs are 8 seconds. And then these are the values. The absolute, of course, always positive. The relative can be positive or negative as we go along. If we're to highlight this column, we can see that that graph will mirror what we saw in the trends. So that's exporting trend values. This will again be dependent upon what you're exporting. If you're exporting FFT spectrogram values from 1 to 20 hertz, you'll have 20 columns for each set of trends that you have. If you have left hemisphere, right hemisphere, you'll have 20 columns. Each one will be 1 hertz for left hemisphere, and another 20 columns for right hemisphere. Asymmetry spectrogram, you'd have one set of 20 columns showing the asymmetry at each frequency. So anything that you're seeing in the trends, you can export. The number of columns you have really just depends on what you're highlighting and exporting, either single values or multiple values in the case of a spectrogram. Now, what else can we do? One of the reasons that we're going to export values is to perhaps apply statistical analysis to those. And that can take a bit of work in multiple programs. Now there's a new feature where you can do a lot of that work within the PERSYST software. I'm going to go ahead and switch this to a comprehensive Z-score trend pattern. And we're going to page to the beginning of this, and we'll leave it at 2 hours. There's a baseline automatic. It's set when you process the recording in PERSYST 13. It'll automatically set a baseline. It uses some asymmetry spectrogram, or rather Z-score spectrograms configured for looking at recordings. You can create statistical trends for just about anything that's trended in the software. But let's start with these. This marked a baseline automatically at the beginning of the recording during this particular state. And the way that this is scaled is increasingly red means there's more of it, higher Z-scores, from that empirical null. And white means it is no statistical variation from that empirical null, and increasingly green means you have less of it. Since we're rendering these as spectrograms, let's go ahead and turn on the scales. They go 0 to 20 hertz. Instead of showing you the values at the moment, like we're seeing up here in the left and right FFT spectrograms and the asymmetry spectrogram, these are showing what is the difference at that point, where we're having to be clicking, versus this empirical null. What's an empirical null? What it does is it's a normalized z-score. It's essentially saying, all right, whatever the frequency distribution of frequencies and amplitudes at this particular marked range of EEG, that'll create a baseline that will calculate z-scores that is unique to that baseline to mark for the patient. So if we create a different baseline, those z-scores will be different because we're comparing to a new empirical null. Well, what does that look like? Let's pick another stable part of the EEG, and let's zoom out. Well, let's go to an hour. And the reason we want to use a stable part of the EEG is this. If you're comparing statistical variation, and there's a tremendous amount of variation in the range that you've marked, it's not going to really show you very much difference because your baseline has so much variation in it. So you want to pick something that's fairly stable. Not make it too long, too short. You want to have a decent sample size. 6 minutes is a pretty good range to use. You can use a bit more, a bit less, but again, you want to have enough samples that that null that empirical null reflects the content of the EEG pretty nicely. So let's go ahead and pick a spot. This range here looks pretty stable. I'm going to go ahead and select new baseline, and I'm going to mark it to that extent. I'm going to add the baseline. I'm just going to call it pre-clamp because that's what it is. So now it's calculating differences from that new empirical null. Let's go ahead and zoom out just a little bit to 2 hours. So we're looking at left anterior, left posterior, right posterior. So we're looking at frequency by quadrant, but we're not looking at the absolute values. We're looking at what is the difference between wherever we happen to be looking and that empirical null that we created by marking that range. So here's before the clamp, and then here's after the clamp. Well, it's turning very, very green, indicating there's a lot less of whatever there happens to be in this baseline. And if we look here, we can see that mostly in the lower frequencies that we're losing a lot. Let's see if we've set the baseline a little bit closer to the clamp. So I'm going to go ahead and delete this baseline. Let's get a little bit closer to that. Pre-clamp, post-clamp. Sorry that the mouse is jumping around a little bit here. All right. This is where that second change happens. We can see right posterior, loss of faster frequencies in that beta to alpha range showing up in that change spectrogram versus this. Well, let's go a little further. So instead of marking something pre-clamp, let's mark it during this fairly stable range after the clamp, because we've got pre-clamp, we've got a little bit of rebound here, and then this fairly stable spot. Call it post-clamp. So now we're comparing versus this, and a little bit later on, again, this is that next change where we lose a little bit more on the right. You can see the shadowing here. It's turning a little bit more blue to green, indicating a loss of frequencies at that point. So the idea is that longer recordings, very long recordings, 24, 36, 48, 72 hours, even spanning recording segments, you can mark a baseline according to patient state, awake, asleep, post-in, where you go to mark, and you can calculate differences from that point, even if it was many, many hours prior to. That's something that if you've got very slowly evolving changes, these are not that slow. If you have very slowly evolving changes, you can visualize those. Perhaps nothing's happening over a 4-hour period, but it might be very different from something that happened 24 hours before. And so that's the idea of the being able to mark baseline, create an empirical null, and calculate differences from that, wherever it happens to be in the recording. But there's context. So in other words, if we're comparing awake and asleep, obviously those would be different. So we want to keep in mind patient state.